All right, hello and welcome back to Evans Imagines 4, episode 7, where we examine the cutting edge. And as usual, we're going to start with the homework from last time. We're going to start with the difference in types of neutrinos. So we have Dirac and Majorana neutrinos, where homework question number 1, what's the difference? How far away can our current detectors find them? And what do they tell us about where antimatter stars are? So the difference between Dirac and Majorana neutrinos is twofold. Majorana neutrinos are their own antiparticles, and they don't have mass. So Dirac neutrinos is currently the model that's thought to be what neutrinos are, in which case there are antineutrinos because they have a slight mass, which slightly breaks the symmetry. And so that's the thought. And so when we get neutrinos from a faraway explosion, we expect them to be the exact mass signature of the explosion of the star. So we know that even though we don't know the light signatures of the different stars, and we can't tell an anti-star from a star, when we look at the light, when we look at the neutrinos, we can't. Now, granted, they have mass, so they're not traveling quite as fast, whatever. But we do have, let's see, we can tell stuff from not that far away. So I have it at the end of this lecture. Now that I see it's in the homework, I should probably pull it up towards the beginning of this lecture and pull it. Here's the super K. So, because I thought this was a little bit more confident, a little bit more fast. But yeah, super K limit, 95 confidence interval, 95% confident that you would see a supernova of a standard energy. It's not that close. And so, it's like half a megaparsec. So like I was saying, that 5 megaparsecs is the different distance between galaxy clusters. So, if we assume that a cluster is called a cluster because it's all made of the same type of mass, then we don't really know anything from the, knowing that our cluster is made of the same type of mass, because we already knew that it's attracting itself. That's why we assume it's attracting itself, and why we assume the other stuff is not attracting itself, dark energy, etc. Okay, so you'll see a graph in a second when we start sharing. But let's go on to number 2. I want you to read about the Muonium Anti-Gravity Experiment proposed by Professor Kaplan and Phillips, and explain the expectations of a balanced state of positive and negative mass that's equal. So positronium, muonium, all of these examples are good because they're one positive and one negative thing in a particle. Now, they're not bound together by gravity. I realize the way I worded the question, you might think that they're bound by electromagnetism. So, right, because everything's negative about them, not just the mass. And that scales, like it's way more important. So, and then number 3, so yeah, right. So reduced mass, we need to talk about number 2 a little bit. Where's oh yeah, put that there. So if you think about like what it means, like if you just plugged into the reduced mass formula, the M1 and M2 with a negative, like, we're being Bondy for the situation, just plugging it in without thinking about it. We get something over nothing, right? You're an infinite or not a number mass. So I looked it up. We do have vibrational spectra for these. We know they do not have an infinite reduced mass. So that means the harmonic oscillator is, yeah. So it's not the right kind of mass, though. That was the trick question. You wouldn't plug in the M's like that because that's gravitational mass. And this is an inertial mass, and really there's only inertial mass. And like, I mean, aside from when you're dealing with gravity, in which case you have to worry about gravitational mass. But in general, you do not have to worry about gravitational mass, thankfully. And then the last one, there's this paper. It's just so nice. I want you to go read it again. If you didn't see the last lecture, check out this 1898, the first reference to antimatter that's really, what we think of it as now. The exact opposite of matter. I mean, 1898, they just found the electron or whatever, Thomson's experiments and stuff. So they were like, well, what if there's a negative electron? It's not really that insightful, but it is historically accurate. So let's share screen to the, okay, it's the wrong button to press there. Okay, sharing lecture, boop. All right, slideshow. Let's do it. So welcome to this lecture. I just told you guys about the homework. Well, you could see my big, beautiful face, by the way. like, subscribe, and share. You've made it this far, so you are enjoying it, but also whatever, just enjoy it on your own. Do the homework, have fun. Homework review, this is what we just talked about. Yeah, don't get tricked by inertial and gravitational mass. Pretty much everything is inertial mass that we know about, and so then we have some gravitational mass questions that are hard. Super K limit, this is what I was referring to. I'll show you the graph, and I'm just relying on these other guys' calculation because in so doing, these are the probability of seeing certain events, right? So that's all I wanted to know. So I found an example in the literature, and yeah. Actually, yeah, this is even better. So this is constraining not just what super K can do, but what a theoretical bigger version of super K could do, right? So that's pretty cool. I hadn't noticed that before, but either way, we're not going to be able to know really the episode curve. Yeah, so that's the difference. So this is a 1 megaton detector up here. We would definitely know like about, well, 2 megaparsecs. So we would know about 5 megaparsecs away with like, we might see one every now and again if one happened. So yeah, a 1 megaton detector is pretty solid compared to the super K, because super K is here in the, you can see 1 megaparsec, we're talking, you get down to gravity cluster, what do they call it? Galaxy cluster. Distances, there's just no possibility that we're ever going to see it, even if you built the bigger detector. You know, I think I did a calculation once that if you filled like all of the world's chlorine or something in a theoretical sphere of arbitrarily large size, it gets pretty big because, right, you have to get, you want it, ideally you would have 95% detection probability beyond 5 to 10 megaparsecs so that you're making sure you're into that next galaxy cluster and seeing all of the supernova there, because that's when you expect to see a bunch of anti-supernova, right? But that's real big, right? This is the difference between, so yeah, it took going up to 1 megaton to get here. So if we wanted to move it to here, we'd probably have to go to, I don't know, a gigaton. What's that? It's much bigger. So it's an absurd proposition. I'm not really proposing it, but that's where we'd have to be to get serious about measuring this with neutrinos. And even then, even once you build this thing that's like, what is this? 10, 100, 1000. So if you did build 10,000 times the biggest thing in the world, you still wouldn't be guaranteed to find it, right? Because then you still need it to be Dirac. And what if there's another reason for the neutrino oscillations? Then you're in trouble. Because people do still think they move close to the speed of light, and they can't move all the way there if they have mass. Okay, we're getting some weird latency issues. Sorry for that. Okie doke. So, let's see. Can I move this at all? Let's see. Oh, well, that's cool. Probably would have done that a long time ago if I know you could do that. Okay. Well, it shows how much I try things. Okay, cool. So, right, we're getting back. This is my to-do list of things we're going to talk about. And this lecture, well, I guess we're going to come back to number 1 next time for the next lecture. I was like, this isn't the one where I ripped Bondi the whole time. So now I'm too big up here. But if I fix this? Yeah, theory experiment. Okay, that's fine for now. And then we'll explore. That's cool to know I can do that. Then we can explore the misinterpretation of saying, introduce Lagrangian. We're going to do 2, 5, and 8 later in this lecture. And they used to be like on my to-do list. Now they're marked off. So this is an active to-do list. And I'm going to cross off stuff. I'm going to add stuff. Death Star. Death Star needs to be on this list. We need to talk about it in this class. Number 11. There is a Death Star implied by all this. There's a lot of defense applications that I'd rather not exist, but they are there. I click the button. Okay. So yeah, these are the ones I like. For now, kind of my favorite. What we're going to do now is we're kind of going to take stock of where we're at, because we got a kind of crazy theory. I'll grant you it's pretty nuts. And we want to defend it to others. And we want to know which others, right? And because like you need to defend different parts to them. And so we're going to just take a little step back and prepare you for the various types of person you might encounter who are out there and thinking about these issues, and basically prepare you to beat them at an argument where they are clearly better than you at their subject. You got to make sure to let them know that you know that, because they like that. But okay, so things that I like for now, I think we would all agree at least needs to be taken again from first principles, with the exception of a couple of labs who have already done it. Number one, the Lagrangian for antimatter. Got to rethink that. Add that to the field equations carefully. Possibly reduce it further with an approximation. I already indicated on the last list. We're going to do that. And then look up the gravitational and inertial mass of virtual pairs and what does that affect. So I think there's no gravitational mass to virtual pairs, so I don't worry about that result. We can put that against anybody, any of these categories of people who might object, particularly quantum field theory guys are going to really talk about those more than your general relativity guys. Meson similarity. Okay. So let's talk a little bit about what audiences are going to respond to our negative mass antimatter arguments and how they might respond. And then let's give some counter arguments to each point. You know, playing 11 dimensional chess here, and just trying to keep up. So if we're talking to general relativity guys, you have to know those general relativity guys are going to love Bondi. They're going to love Einstein. The Einstein field equations are where they're going to start with this. So if you're going to change something about those, you got to have a real good reason. And once you do have a real good reason, they're going to be the most important place where the paradigm plays out. So general relativity guys, yeah, welcome on board whenever you want, but obviously you love Einstein a bunch. And part of this rant is eventually that your whole thing, this field equation, is more or less a local approximation that works in the cluster exclusively-ish, right? Like it works really well, really close to here, and that's fine and good for now. But everything isn't really close to here. So when you build a big equation with everything in it, it might not be the right approximation. So anyway, quantum field theory guys, they're going to like the Feynman parts of this. They're going to like, the graviton being part of this. They're going to like the unified theory taking another step. But they're also big CKM guys. They've got some predilections here towards other basis sets that are already in place. And it's an elegant solution, right? We talked about that idea of being slightly off the off diagonal or whatever eigenstates. And so I think that's a little bit of a weak spot that we need to keep, talk to them about. But, I don't know how you choose your battles there. But yeah, I'd like to. So I guess with the QFT guys, I'm talking to them about ML good more than I am the general relativity guys, because that's a way out a field for them. They don't care about mesons. But if you care about mesons, we need to be talking about mesons, because there's a big thing to talk about with mesons. Did I have it on the 1 through 10? Jerk of the universe. Yeah, we'll talk about it. The jerk is another name for the derivative of the acceleration. So I have a good long rant about the jerk of the universe. Okay. Cosmology guys. Oh, right. Cosmology guys, I've given them a lot of credit throughout the course of this class because they are quick to overturn the paradigm in favor of something that makes more sense. Particularly, they found the dark energy and the dark matter. They're the reason we're talking about it. They had the early universe too. A lot of interesting things that I like to think about coming from these cosmology guys. So I think they're prime territory for when you have a new paradigm and a shifting paradigm for testing if your theory passes muster, because a lot of these new paradigm theories have come from them. And yeah, that's how we tell if they pass muster. Then you got beyond standard model guys. So people who are already thinking about revolution and like they've got their own theory. So less overall heft. So what I'm saying is, yeah, it's a lot of work with the beyond standard model guys because they all have their own theories and everybody's reinvented everything. So they've reinvented calculus in their theory, or they reinvented every law in their theory. And you have to go through and make sure that it's fine and that it is meaningful. And so it's kind of fun. I mean, like you got multiple 100-page treatises you're going to have to read, but You know, you got non-commute, you've got commuting operators where we don't normally have commuting operators. You've got bit strings, all sorts of cool ideas that are worth your 100-page read, and like trying to work out in that approximation some fun stuff. Because I mean, who knows? Some of these things might just be a different interpretation of whatever reality. Like, I'm not convinced that there's like a discrete versus continuous fight to be had. I don't really have a team, so you know, yeah, can't really. I don't think that fight works out very well. But okay, so what idols are going to be involved? Did I have right? Good. I was like, I think I should probably have a more classic page on this. So let me make myself a little tinier while we look at this so that I can remember what's up here. Okay, so general relativity guys. Yeah, if you're ready, if you're trying to talk to them, you need the background on the field equations. So we'll talk a little bit more about it at the end of this lecture. And if you're happy with what you've read, then don't worry about it. Don't keep reading stuff. If not, go get Misner. It's a big book. I think I took it back to the library. Yeah, I don't have it with me here right now, but you can read it. It's fun. He's got a very, very good explanation of topology. I think the closest I've come to understanding what's going on in a physical way that makes sense to me comes from that book. It understands why people are using it. But boy, it's so big. And for being so big, it has so little discussion of negative mass. So I don't really have much to say about it here in this class, except go read it if you want to talk to general relativity guys, because you'll need to reference stuff there if you want to convince them of stuff, because most of them also have this or a similar book as the basis for their understanding, because they need that feeling, right? So the feeling came from somewhere. All right, QFT guys, for them, you'll need to read all the background on their gauge theories. So through at least the reduction of the E and B field to the A and phi, I think that's, for me, what makes it convincing. It eliminated parameters in one of the theories that I knew from high school. So I thought that was really cool. And the fact that it goes further and does some adds weak unification is pretty cool, and suggests to me that maybe we can do more than just electroweak unification. So yeah, and I think strong force is just, there's a millennium problem like about that. So we're getting close with the strong force. Cosmology guys. So if you want to talk to cosmology guys, then you have to read all their beginning of time stuff. I love it. Make sure you read the Cliff Notes version at least, so you know the first 3 minutes by Weinberg. You need to know boson photon ratio. Ugh, gross. Escape out of presenter mode. Thought I fixed all these. Boson, where is it? Boson. Baryon. Yeah. Hey, you guys, you all need to know this. Okay. So back to the slideshow now. We fixed baryon photon ratio, which is the thing I'm actually trying to talk to you about. And the reasons for the various part of the cosmological standard model. Hint, they're kind of patched on. They're not really reasons. They're more or less. Every time something pops up that's a falsification, we slap it down and we say it's no longer a falsification for this or that reason. Yeah, so I'll go through cosmology guys stuff and get ready for a fun time, because they've got a lot of good theories there. I don't think I have anything. Yeah, know the words hyperinflation, anthropic principle, symmetry breaking. Yeah, and what is the reason for all of these things? So just quick review, because why not? Hyperinflation is, it looks like in the past things were getting thrown apart a lot faster than they are now. So why is that? Currently, Guth has an idea called hyperinflation. It's kind of also a little cheap, so I'm not going to go into it further. The anthropic principle, the idea there is that, and symmetry breaking, so they're kind of hand in hand. The anthropic principle is the idea that, well, why is there a little bit of an excess of matter in the universe? Because we're made of matter, so we have to be in a matter universe. To some people, that's enough, but to me, that's very, very childish. I don't like it at all. And the fact that that's our only motivation for symmetry breaking, which is otherwise very, very, very rarely observed in nature, is a mistake. It's a kind of mistake we've made before. It's a very heliocentric or Earth-centric, whatever was before that mistake. I don't understand it. I don't understand how we're making it again. 5 and 7, what am I? Oh, I'm referencing the topics, right? So for the various topics, we're going to have these various guys, and we'll be able to make our various points that will be convincing to them. Probably should have had the 4 or 5. Yeah. So yeah, the things you want to talk to the various guys about. Yeah, this is a tough page to interpret without that other page near it. Beyond, yeah, you just got to read the theories for the beyond standard models guys, and can dig into more common theories like that. Complex mass, Dirac Milne, Bondi models, Hoyle-Nylander. If you want to read the, I didn't give any of the ones that anybody knows about. So these are just the ones that I read about / that I like. So yeah, so I think that supporting arguments for my theory are greater than for the Bondi derived theories. You can see on the list of supporting arguments, the bold ones are the ones that are just for my version of it. And a lot of them are graviton related, CP model, or the meson thing, early cosmological model, photon to boson ratio. Oh man, how many times did I put this in here? Sorry guys, I have to fix it every time. Just hate to see this. Photon baryon ratio. You know, I was thinking about, I was like, I should probably Google and see, am I saying the right word there? I don't think it's boson. It's not boson. You're thinking of something else fun that you like to deal with. Okay. The Dirac prediction. So the idea there is that if these pieces, like for instance, if we examine our cluster and everything else, and each place in time, or each place in the universe has a our cluster and everything else, then you've got everywhere the prediction of pushing apart. And over time here and the average of everywhere else is getting further because of the pushing. So you have the prediction of negative jerk, because this should be the largest scale force in the model. So there's not going to be any tail force besides it. So it resolves a lot of problems with only 2 changes: symmetry, negative mass. It's a lot. Negatives aren't complicated. They're like one of the first things we did as numbers. So why not put it here with mass? Seems easy. Yeah, so I think it's a good theory. I think you can tell all your friends about it. I do think, you know, oh, okay, we'll go over the opposing arguments. I feel like I've done this slide at some amount of length at you before, but if I have, forgive me. And if not, you know, congratulations, you got to hear this rant. So these are the problems that still bother me. Number one, why do Majorana particles follow only one geodesic? I think it's because they don't have mass. So a negative of 0 is 0. So of course they're the same. But why do they feel positive and negative mass the same way? I guess why do they feel assumes they do, which is an interpretation thing. So I just have to know my astronomy better. My cosmology, I guess, is what it is these days. But so I got to figure out for a lot of these guys what's going on, and then fix it. So then CP violation in differs in magnitude across mesons. So that's what I was telling you about. Goldman told me about that one. Where are the neutrinos? Right. So this is what I was telling you about at the beginning of the lecture. I'm not really worried about this because of the range, right? It's we're not going to have bigger detectors for a while. Sure, this is good motivation for bigger detectors, but they got to be real big. So either we're going to make a new thing that's like neutrino juice and doesn't need as big of a detector. I don't know if that's a thing. I think these are already pretty good neutrino juices. And then, yeah, so we can build them fine. We've got something to look for now, but it's going to be a while, or it's going to take a big anti-supernova like that you could see with your eyes probably anyway. So, I mean, I guess it'd be good to have the anti-neutrinos. Disagrees with Einstein and Bondi. Equivalence principle. Maybe you're an equivalence principle guy. Can't ever get here because of the equivalence principle. Not a problem for me. So, you know, I just don't. I'm not beholden to that idea as is. Like it begins with the clause, everything but all forces besides gravity. Okay, well, I bet this becomes a problem later if we leave it out. So probably include it now. Massive virtual pairs. So this is something Feynman brought up. This is something Weinberg brought up. If you got a smart guy and you bring up this idea, you're going to bring it up. So you got to know your responses. What kind of mass we're talking? Gravitational, because that's all we're talking. We think that opposite masses repel. We're not talking inertial mass. So then let's see. Then we have the Opvos misunderstandings. Yeah, no, I'm not worried about that. Lots of certainty is very seductive to some scientists. They like to do more and more complicated experiments, or more and more not complicated. They do detailed. I don't know. Anyway, so there are a lot of good Opvos experiments, but they're all with matter and matter, so we don't find out about anything but that effect. And it's going to be hard because you wouldn't call yourself negative mass. So that's why I would replace the equivalence principle, where you can't tell whether the acceleration is due to gravity or force, to being you can't tell if it's due to gravity or gravity from a matter thing, or gravity from an antimatter thing, or a force. So you can't tell if you are matter or antimatter until you know you're matter or antimatter. Part of the setup to the problem is the elevator and the planet you're falling towards are all made of matter by construction, and everything in the universe is too, because of the anthropic principle. So yeah, how do I get there from this list of things? Can't pull myself back. Gamma ray questions. Yeah, these are, oh yeah, Yavos, sure. So you need to do more Yavos experiments with antimatter. You need anti-apple, and you need to sling it around in circles and stuff around the Earth. Okay, so gamma ray questions. These are still open to me. Negative mass calculations. So we need somebody to do the patchwork calculation, patchwork universe paper from Glasgow needs to be done again. If you are a graduate student in his lab, then do it. We need that to be done right now. So yeah, that's what I would suggest there. Lack of direct observation. Right. So that's, people will bring up that we haven't seen graviton, we haven't seen negative mass fall up, and that the alpha experiments. Let me tell you, if somebody cites the alpha experiments to you as evidence for they're the Vos experiments, Vos, whatever. And I apologize, I'm really bad at names. I'm not an announcer. This is like my first attempt at ever talking on camera. So there's going to be mistakes like that. Please forgive me. For instance, apologies to Dr. Heald. I appreciate your time, and I'm not trying to mess up your name. Graham. Okay. So thank you for all of your work, everybody. Apologies if I mispronounce your names, and I do appreciate your work. That's why I like to bring you up anyway. So unfamiliarity of antimatter. Wait. Lack of direct observation. So there are a lot of experiments. Like I say, we got 3 or 4 of them. So fine. You guys can bring that up if you want to be proven wrong in your lifetime. We can make a wager. Hey, if someone brings up lack of direct observation, then we got time. We got time for a grand wager. I don't know, bottle of wine, something fun for, a few 100-year question being answered. That's the way I think science should be. Like I say, there's fun parts of academia and not fun parts, and that's the fun part. Unfamiliarity of antimatter. So yeah, people don't like it. They haven't seen any of it, and because they haven't seen any of it, it's weird that there is an equal amount. So just like people don't like the many worlds theory because they don't think there's a bunch of little thems running around, they don't like the idea that there's an equal amount of matter and antimatter because they haven't seen it. It's not here. Pop, 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 pop. This is people's folk physics coming in, right? That's why we have the physics we have. It comes from folk physics that built into us, where we're like, well, God exists for us, right? Because we're here. Well, not really. Okay. Higgs focus. So some people will be like, well, the Higgs says we got to do this or that. Need a break, guys. Higgs doesn't tell you to do anything. You guys made up the Higgs because you got squares in there too. We can talk about those at a different time with a different guy. So yeah, that's not me really. Higgs guy is probably a more mathy guy than me. I'm not a math guy. I'm a science and physics guy. All right, so remaining mysteries. Let's get me a little bigger here I think we're getting towards the end now. So get some more Evans in your face. I don't know if this is actually changing on the video or not. I've never done this before. So the remaining mysteries, we got too many fundamental constants. Anytime, any theory that eliminates a fundamental constant, for instance, I just was reading through McGovern's theory in prep for a call, and marking this thing up. Always enjoy to do that. And found out he's eliminating at least one constant from nature using a cool little theorem. So calling it little is very, very rude. But that's cool. That immediately gets my attention. I haven't seen other versions of that. Like whenever I read other people's big theories, they don't eliminate complexity. They add a lot of complexity with and get nothing back. So I'm happy to have gotten something back. What's up with the neutrinos? So I don't know. We'll have to find out. We'll have to see supernova. Hopefully not too close, so a little far away, but close enough that we can get some neutrinos from it. So that's a pretty fine line to be crossing or to be walking. Neutrino oscillations have been used to infer mass, but lots of other explanations for that. Beginning of time. So that's one where I think we're onto something. But I still need to do the calculation, and it's not on the list, it's at the very end of the list. So we'll talk about it. It needs to be modeled just to see if it really does look like hyperinflation. Like I think it would look like, I think MOND is another word for it. So modified Newtonian gravity, something or other, basically. Yeah, then there's a hierarchy problem as well. And that's for math people, because like I said, I'm not one of y'all. Screen sharing. Yeah. And recording. Okay, good. Just making sure. All right. So now we'll do the last little Lagrangian hunt. We're going to do the first couple things on the list that I have crossed off. So we're going to do misinterpretation of Singh. We talked about that already, so I crossed it off. Now we're going to introduce the Lagrangian for antimatter and talk about the Einstein field equations real quick at the end of this lecture. Because yeah, it's been a while. I lingered on a lot of these slides that I don't think I was supposed to linger on and talk to you about before. But this is a pretty cool. Oh, can I zing myself over here to the other side? Sure. Oh, that's kind of cool. I'll start doing this all the time. Okay, so this guy Ulrich has a bunch of cool papers, and in particular, he has a very nice version of the derivation of the particle-antiparticle gravitational Hamiltonians. I like this almost 100%, this paper. I recommend you go read it. But when he gets to the part plugging in the potential that the particle and antiparticle feels, he falls into the Bondi trap, and he gives the Bondi version of this case. And so I just want to point out that there is a alternative solution, and yeah, you can you get a plus like inside. Like the relative relationship here changes relative to the you're making an assumption about the relative sign SIGN of MI and capital M when you plug this in. So we have to be very explicit about that. I have a paper coming out about that soon. Look out for my conference proceedings with Mills. Yeah, and like I say, I tried to get into what's going on here, but field thinking I think might be a problem here, right? Because this is a very standard way to look at this, but when you think about MI and phi, that's not really the situation. You have a mass and you have two things, and you don't have so a field, I'm not convinced it works for reasons of being necessary so much as sufficient for calculation purposes when it is convenient. Yeah, this is another Feynman point. I've mentioned Feynman's an idol. I don't know if I've mentioned he made this exact point about he thinks the field equations are an approximation. So let's see. Yeah, I don't want to go into this too much because, like I say, this is not published yet. But I do want to again say, please go read this Ulrich paper. He's really sharp. All of the introductions of inertial mass are correct. His identification of which things in these Dirac equation is inertial mass is correct. The problem is the coupling. So he thinks about the coupling. And specifically, he cites Singh following some of the other guys who have cited Singh before, thinking that you have to recover the Bondi result. And that's not right. Okay, I'll read this later. I was getting a little bit into reading it, and we're right at the end. So let me give you guys like a little bit of homework. We're getting to the edge list. Go ahead and pick a question from the list if you dare, and get back to me about it. You can even think about the Death Star if you want. How's the Death Star factoring into things? Yeah, number 2 is kind of what I did there at the end. If you want to punch that up, send it to me, that's fine. What is the number 1? What is the moment of inertia's relation? Yeah, so just feel like I gave you this question already at the beginning of this lecture. Oh, no, okay. Sure. So now I want you to go ahead and actually do the problem with the rigid rotor. So look it up on Wikipedia. It's related to what we talked about last time, but you can look up reduced mass and all that and solve it to your satisfaction. So I will stop the screen share to make myself a little bigger and say thank you for joining us again on this episode of Evans Imagines. And join us next time when we will talk about some more of the cutting edge. Yeah, and whatever I want to. So see you soon.